Hi everyone, and thank you for coming to this talk on fault networks in Malawi, and thank you to the conveners for the invite as well, and also to acknowledge the various long list of collaborators whose work I've drawn from in this presentation. So when I'm thinking about normal fault networks in Malawi, what I mean is instead of kind of investigating each fault individually, I'm thinking of these faults as kind of a single group of kind of interacting faults. And using that kind of approach, we've been able to learn something about the kinematics of the faults in Malawi, their slip rates, and the seismic hazard as well. And in this talk, I also want to kind of go through turning that around and what the fault network in Malawi might tell us about other normal fault networks in terms of maybe how normal faults grow, and kind of capturing this information in fault databases. So just to kind of clue you in with where we are, we're down here in the kind of southern incipient end of the East African Rift Western branch. The closest surface volcanism is the Rongwe volcanic province in southwest Tanzania. So we can generally consider this to be an amagmatic section of the rift. And for the majority of the talk, I'm mainly going to be focusing down here in southern Malawi, and then at the end, kind of discussing how we've started extending our analysis across the entire length of the country. So up to really a few years ago now, really very little was known about the East African Rift in southern Malawi. There was an active fault had been described along the Balile-Matakataka fault, but really the fault mapping was quite crude, and it was really quite unclear what the extension direction in the rift was. So originally based on fault sicken sides, a northwest-southeast extension direction had been proposed. Initial geodetic data indicated it was maybe more east-west, east-northeast, west-southwest, but that was really only based on just one GPS station. And earthquake focal mechanisms kind of indicated that it was a northeast-southwest extension direction. But again, this is only really based on about 13 focal mechanisms across the entire length of the country. So when we first started working in southern Malawi, kind of the first approach was really just to kind of systematically map the active faults, to define the fault network, which we mainly did using high resolution digital elevation models. And you can see some examples here of revealing like really textbook interactions between kind of active fault scarps and footwall eroding streams. And then we're also able to ground truth these observations through 2 field seasons in Malawi in 2018 and 2019. So we kind of collated this information in what we called the South Malawi Active Fault Database. So hopefully you'll agree that the fault mapping in this database is a little bit more refined than it was a few years ago. And also for each fault, we've added some attributes in terms of how it was mapped and the geomorphology of a fault, which are modeled on the Global Earthquake Model Global Active Fault Database. And this database is readily accessible through the journal webpage for Solid Earth. But I would also highlight that this is not a complete active fault map for Malawi. So in ongoing work with Fola Kolawale, we're looking to identify kind of blind faults in Malawi. So faults that don't have a surface expression, so they wouldn't be identified through digital elevation models, but we can identify through aeromagnetic data. So with this fault network now defined, we could start asking some of those questions that we had before about the rift. So one of them was about the extension direction, or more specifically here, I'm thinking about the trend of the minimum principal stress, sigma 3. So to kind of address this question, we kind of asked ourselves, well, what are the range of sigma 3 trends that would allow, the variably striking normal faults in the rift to reactivate? And so we calculated what we called the effective coefficient of friction, so kind of the maximum frictional strength that would allow all these 3 faults to reactivate without also inducing failure along an optimally oriented plane in intact rock. And we calculated that as a function of sigma free trend, and these are the results here. And essentially what it shows is that if you kind of got a north, east, southwest sigma free trend, or a southeast, northwest trend, then you need quite frictionally weak faults or kind of high fluid pressures, neither of which are consistent with observations from the field of the fault zones in Malawi, or also some experimental deformation experiments performed on samples from the rift. Instead, it seems to suggest that, to get these faults reactivating, you need a sigma free trend of kind of east-west, east-northeast, west-southwest, which is kind of consistent now with some more focal mechanisms from the rift, and also new GPS data, which includes more GPS stations in South Malawi. Another question we've also been considering is, what are the slip rates on these faults? And so ideally, you address this question, you'd collect, kind of stratigraphic on-fault data. And I'm not for a second suggesting the approach that we've taken is better than that, just saying that, in the context of a 3-year research project, we're not going to get the slip rate of 20 faults. So we're going to kind of work with the data that we do have, which is the extension direction, regional extension direction from geodesy, and an idea of how that extension might be distributed across the rift, across the normal fault, across the large rift bounding border faults and the smaller intra-rift faults in the center of the rift. And that's kind of encapsulated in this equation here, where the key parameter alpha is alpha, and that kind of just describes how we're distributing the regional extensional strain between border faults and intrabasin faults. So in terms of setting that value, when you look kind of elsewhere at kind of low strain rifts like Malawi or in analog experiments, you tend to find that a lot of the extension should be on the rift border faults. So the faults with the big, large escarpments, reasonable value would be about 80 to 90% of the extension. When we looked in southern Malawi itself and used scarp height as kind of a proxy for extensional strain, but actually we found a little bit more of the strain might be on the intra-rift faults, up to about 50%. So there's kind of a bit of uncertainty and alternative hypotheses here for applying this equation. So we kind of used a logic tree to kind of explore some of this uncertainty. And overall, it's kind of suggesting that the slip rates on the border faults are about 0.5 to 1.5 millimeters per year and about 0.1 millimeters per year on the intrabasin faults. Obviously, there's quite a lot of uncertainty in this when you go through all the branches in the logic tree. A lot of these extreme values are probably quite unlikely, and we're currently working at the moment to do kind of a more statistically robust analysis of these uncertainties. But in the meantime, it's quite useful because we've defined the slip rates on all the faults in this network in kind of a self-consistent way. And it can allow us to kind of identify maybe the most dangerous faults in Malawi in terms of faults which have a high slip rate and are close to densely populated regions. If we want to start thinking more explicitly about seismic hazard, though, there are a few additional steps which should be explored in this part of the logic tree here, where we started considering applying empirical scaling relationships between fault length and earthquake magnitude, and fault length and earthquake single event displacement. So with single event displacement, we can then combine that with the slip rate to get an idea of the earthquake recurrence intervals in Malawi. So that's telling us you get quite large magnitude earthquakes in Malawi, but because these are low slip rate faults, these are infrequent events. And I should also mention that you can't always assume that a fault is going to rupture its entire length in an earthquake. It might rupture in kind of shorter sections where you've got geometrical complexity. So we've tried to identify some of those geometrical complexities in the fault network in South Malawi. So they're shown by the blue triangles in this map, and also try to identify where maybe you've got closely spaced faults across strike that maybe they might rupture together in kind of a multi-fault earthquake. And so there's quite a lot of uncertainty and kind of subjective decisions that we're having to deal with in this analysis. So when we've compiled it, we've kept it separate from the kind of more objective active fault database and collated it separately in the South Malawi seismogenic source database. Okay, so kind of moving on now to kind of extending this analysis across the rest of Malawi. So this is kind of ongoing work, is to extend our South Malawi fault map across Lake Malawi using data from 2 generations of 2D seismic reflection data, Project Probe and Segment. And this basically is giving us an idea of where all the active faults are in Malawi. And it's giving us really now quite a large group of faults, and we can maybe start doing some kind of analysis of this fault population to tell us about the fault network in Malawi, and maybe what it might tell us about other normal fault networks as well. So one thing that we've been considering is the fault length cumulative frequency, which I've plotted here in log-log and in log-linear space. So these are quite complex plots. Maybe so just to kind of walk you through what they're showing is we initially considered that each of the faults in Malawi represents a distinct fault, and we've plotted the cumulative frequency of those of that population in black here. But we've also considered that maybe some of those faults which are kind of on echelon with one another, they're kind of cross strike and only a few kilometers between them, they might actually represent maybe kind of a single coherent structure. So this kind of multi-fault hypothesis, the cumulative frequency of faults mapped in that way, we've plotted in red. And then we've obviously plotted best fit lines through both of these populations. We've also recognized that around about a length of about 60 to 80 kilometers, there's a bit of a break in this, and that maybe they're better described as kind of 2 distinct populations of faults in Malawi. And the best fit trends for that we've plotted in the green and blue lines. The key thing I want to come across really though with these plots is that however we kind of play with this data, however we try to analyze it, they always seem to plot better in log linear space, suggesting that they follow an exponential trend.
Yeah, 12 minutes now. Okay,
great. I'm not too far done. So if we're suggesting that Malawi has these cumulative frequency of exponential trend of fault length cumulative frequency, that's quite interesting because where that's been observed before in other continental rifts, it's been observed in quite high strain rifts and more than 8% extension, or where you've got width limited fault growth, but neither of those factors would apply to Malawi because you've got it's a low strain rift, lower than 8%, and the seismogenic crust is very thick there, it's about 35 kilometers. So faults are, when they're growing, they're not going to have width limited growth at up to quite long lengths. So instead, we suggest that maybe because Malawi, the crust there has been deformed over a succession of Proterozoic orogenies, that's allowed a lot of these fabrics have been reactivated by the faults, allowing them to link together very quickly to get kind of a disproportionate number of long faults that you need to get these kind of exponential trends at quite low regional strains. And this might be something to look for in other continental rifts, which are quite young and in deformed crust. So just to kind of finish off, as well as kind of developing a Malawi active fault database, we're also looking to develop the Malawi seismogenic source database, so thinking about the earthquake properties of these faults. So a few more complexities in including the lake faults than in southern Malawi in terms of hanging wall flexure is likely much more important for calculating the slip rate of the intrabasinal faults. And also a lot of these faults in these kind of 3D geometrical models that we've been developing, a lot of these faults likely intersect at depth, and that's going to influence their area, which is going to influence their earthquake magnitude. Long term, the goal is to use the fault network in Malawi for probabilistic seismic hazard analysis. So I've got some provisional maps I'm showing here. I'm not going to go into detail about them. That's basically a talk in itself. But essentially, we're using the earthquake recurrence intervals and magnitudes we calculate in the seismogenic source database and combining that with kind of aerial sources of seismicity to represent the kind of background of fault seismicity, because we're obviously, we're missing faults when we do this. What's quite interesting is because the faults have quite low slip rates, but large magnitude earthquakes, is that they only really seem to be big contributors to the hazard at quite long return periods, low probability. So 2% in 50 years is about a 1 in 2,500 year event. Although this may change with kind of ongoing work through this project. So I'll leave there with some kind of key points and some of the kind of key work that's come out of our project, and I'll happy to take any questions.
Thanks a lot, Jack. There's a few minutes time for questions, and we have the first one by Danielle. Danielle, do you unmute and ask it yourself?
Hi, Jack. This is Daniel Laodavila from Oklahoma State University. My question was, what are the age constraints that you are using for calculating the slip rates on the faults?
The age constraint, so it's the kind of the key parameter for that, I guess, would be the regional extension rate, which we get from geodesy. So it's only essentially been measured by data collected over the last 30 years. So there is obviously a bit of uncertainty with that. Something we're doing is with the lake data, there's a dated offset reflector to 75,000 years. So you can also use that as like another independent way to get slip rates. And so we're kind of combining those two estimates of slip rates to see if they're consistent with one another at the moment. So that's kind of ongoing work.
Thank you. I'd have a question on your definition of a border fault. In the beginning, you discriminated border faults and intrabasin faults, but in the map that you showed, there were some intrabasin faults at the border of the rifts and some border faults in the middle of the basin. How do you deal with this definition?
Yeah, this is a really good question, and it caused us a little bit of pain when we first started doing it. You know, we tried to be as objective as possible and just call it the kind of, you know, a geometrically simple definition of it's the large fault at the edge of a rift. And in some parts of Malawi, that definition, it's really clear, like in the central and northern parts. In South Malawi, it gets a little bit more complicated because there's quite a lot of pre-existing topography there from Karoo rifts. And so we don't know how much of the topography on those faults is current East African rifting. And it might even be even older topography as well from some of the Proterozoic orogenies. So there's some faults which are kind of at the edge of a rift, which really don't look very active, but they have quite a lot of topography on, but we don't think they're border faults because we think a lot of that topography might be older.